Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. We are in the fifth module. We are studying about alcohols and ethers. In the last lecture, lecture 5, we will be studying about preparation and reactions and a few worked out examples of ethers. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at what are the topics that we will be covering in this particular session. We will be covering in this particular session preparations and reactions of ethers, and we will also be studying about some worked out problems related to synthesis of ethers. Let us move on to the next topic, that is preparation and the properties of ethers. Ethers are any class of organic compounds characterized by an oxygen bonded to two alkyl or aryl groups. The general formula is given as ROR. They can be symmetrical ethers or unsymmetrical ethers. The bond angle between ROR prime is actually around 110 degree, and the net, because of the presence of oxygen, there is a net dipole in this molecule. Because of the presence of oxygen with a lone pair of electrons, the ethers may form hydrogen bond with water. In other words, lower ethers are sparingly soluble in water. So because of the hydrogen bond formation of the lone pair of electrons on oxygen, ethers are sparingly soluble in water. Let us look at some of the preparations of ether. The first method is two molecules of alcohol when treated with sulfuric acid and heating produces ether with the removal of water molecule. So if you look at the mechanism, all the reactions with acid catalyzed always start with the same step. The proton is added to the hydroxyl group, which forms the hydronium ion. So this generally can lose the water molecule to produce the carbocation, and this carbocation can now react with the alcohol to produce the RORH plus. This intermediate can be formed. This loses a proton because the bond is broken and the oxygen is electronegative, so it pulls the electron towards itself to produce the ethers, and acidic, because we started off the reaction with the H plus ion, is regenerated in the last step, so it is a catalyzed reaction, and this is the preferred method for secondary and tertiary alcohols ethers formation. And because basically this is a Sn1 mechanism, we already know Sn1 mechanism is favored by secondary and tertiary alcohols. And if we go by the Sn2 mechanism, what happens is this intermediate actually reacts with the alcohol in the rear side attack, with the next step being the same, like instead of water removed in the first step by the Sn1 mechanism, in the Sn2 mechanism it is removed in the next step to produce the corresponding oxonium cation. This loses a proton to produce the ether. So this is the process followed by the primary alcohols ether formation. Let us now look at an important synthesis of ethers, that is Williamson ether synthesis. So in this particular reaction, an alkyl halide and an alkoxide is treated to form an ether. So this is the basic method by which ethers can be synthesized using Williamson ether method. So here Rx is the alkyl halide. This is treated with the alkoxide, that is the corresponding alcohol sodium salt is treated with alkyl halide to give the ethers, and sodium halide is formed. So this is where R is from one, the R unit comes from one of the part, and the second R prime unit comes from the other part. So in between we have oxygen. So the two alkyl units are coming from two different parts. One is from the alkyl halide unit, another one is the alcohol unit. So the alcohol is basically the sodium alkoxide is used. So this sodium alkoxide is formed from the alcohol. So basically the reaction is between an alkyl halide and alcohol. In this particular reaction, the alkyl halide acts like a substrate, and the alkoxide is the nucleophile which attacks the substrate, and the halogen is lost. So let us see the mechanism. So if you have to prepare an unsymmetrical ether, we have two combinations possible. One of the unit, in this particular case, the R prime unit may be the substrate or the alkyl halide, and in the other method, the Rx is the alkyl halide or the starting material. So there is a competitive reaction in this particular case because the elimination due to the use of alkoxide, that is a strong base, is a competitive reaction. So we have two. One is a substitution reaction, another one is an elimination reaction occurring. We have to carefully choose the condition so that we only get the maximum yield of the substitution reaction, that is the formation of ether. So in most of the cases, the primary alkyl halide is the preferred starting material or the substrate because the primary alkyl halides does not undergo elimination reaction. So this is one of the things you have to remember all the time whenever we are using Williamson ether synthesis. The preferred alkyl halide is the primary alkyl halide if that is possible. Here is an example of a Williamson ether synthesis given. So here the primary alkyl halide, that is the methyl bromide, is treated with the sodium tertiary butoxide. So that gives the tertiary butyl methyl ether is formed in this particular reaction. So as I mentioned, for the Williamson ether synthesis, the preferred starting material is the alkyl halide, primary alkyl halide. Now let us look at some of the reactions of ethers. The first one is ethers cleavage by acids. So a ether can be cleaved by the HX acid, which is a strong acid, to give RX and the alcohol unit. So whatever is the starting material can be cleaved back to the alkyl halide and the alcohols. But again, which part will form the alkyl halide and which part will form the alcohol is again a question we have to answer. This alkyl, the alcohol can also be converted with the HX because we are using here a HX, so that can again form an alkyl halide. The reactivity of HX is shown here. Hydriodic acid reacts much faster than hydrobromic acid, which reacts much faster than hydrochloric acid. So the conditions are employed for the cleavage of ethers are concentrated acids, and high temperatures are employed for the cleavage of ethers. Basically, ether group is a good protecting group for alcohols. When we do natural product synthesis or total synthesis, in some cases the hydroxyl group has to be protected because hydroxyl group is a good nucleophile. So in order to prevent the hydroxyl group from getting involved in any of the synthetic processes, the hydroxyl groups has to be protected. So ether group is one of the important group that can be used for the protection of hydroxyl group. So the ethers can be finally cleaved by the treatment with the strong acid, basically HI or HBr. So here is an example of diisopropyl ether getting cleaved by 48% HBr, because HBr is the standard acid which is generally used for the cleavage of ethers, and the temperature used is very high, 130 to 140 degrees centigrade. So we get two molecules of the isopropyl bromide is formed after the cleavage. Let us look at the reaction mechanism for this particular case. So we know ROR, the ether is treated with HX to give RX and R prime OH. So what is the mechanism by which the reaction can proceed? So here the HX is basically the H plus and X minus, but this X minus cannot attack any of these compounds because RO minus is a strong base, but unfortunately which is a very poor leaving group. So this type of cleavage, that is the attack of the nucleophile first to form this alkyl halide, does not happen because that will end up with a strong base, that is a very poor leaving group. So what will be the other mechanism? Instead of X minus, this is going to be the attack of the H plus, or a electrophilic substitute. Electrophilic attack is the first step in this particular case. So the H plus attacks the electron rich oxygen because this has two lone pairs. So this H plus can easily attacked by the lone pair of electrons on the oxygen. So we get this particular oxonium ion intermediate, and this can be attacked in the second step by the halide. So this reaction can undergo by two mechanisms. One is the Sn1 type mechanism or Sn2 type mechanism to produce the Rx, and the alcohol will be formed because in this particular case alcohol is a weak base and it is a much better leaving group. So let us see which mechanism will operate under what condition, whether it is Sn1 or Sn2, we will see now. So for the Sn2 mechanism to occur, what is required is the rear side attack of the nucleophile is required. That is, the X minus has to attack the alkyl group from the other side of the leaving group, that is where the oxygen is present. So if this is a smaller group, then the attack of the X minus can happen very easily. In other words, if this is a primary substituent, then this type of Sn2 mechanisms are very easily possible. So that produces the Rx and the R prime OH is formed. For the Sn1 mechanism to occur, what happens is this particular ion has to undergo slow decomposition to give the carbocation. So if R or R prime is a tertiary group, tertiary alkyl derivative, then they can easily form the carbocation with the easy removal of the alcohol R prime OH. So this carbocation can then be attacked by the nucleophile to form the Rx. So the cleavage, preferred way of cleavage is, if it is an alkyl group, that is a primary alkyl group, then the rear side attack or the Sn2 mechanism is possible for the cleavage, which produces the Rx. And if one of the group is a tertiary alkyl group, then the Sn1 type mechanism is possible for the cleavage. So these are all the two ways by which the ethers can be cleaved. The other part will take the oxygen along with it. Now the next question is, the following alkene is converted to epoxide. So this is a alkene having a trans position, trans isomer. This is treated with peracids. So when it is treated with peracid, what is the configuration of the epoxide formed and are they optically active? So this is the two things we have to answer for this particular reaction. So as I mentioned, the reaction, the starting material is a trans isomer, and we already know epoxidation is stereospecific. It is a cis addition. So in this particular case, this is a cis addition. So that means it is a stereospecific addition. So what we end up is this particular product that will be formed. The configuration of this phenyl carbon and this phenyl group are trans to each other. This product is going to be optically inactive because we are going to get a racemic mixture, 50-50 product is formed. So that is the reason this is actually going to be optically inactive. But the product obtained is a stereospecific product where these two phenyl groups are in trans orientation because they are present in trans orientation in the starting material. And if the same alkene is treated with the chlorine and water and sodium ethoxide conditions, what will happen here? So in this particular case, what we will be getting is basically a chlorohydrin. The chlorohydrin undergoes elimination to produce the corresponding epoxide. So this again is a trans isomer, and this particular epoxidation is also stereospecific epoxidation. So in this particular case, we again get the same isomer in the trans orientation, and this again is optically inactive because we are again getting a racemic mixture. So let us prepare some ethers. We are now going to study about some of the reactions related to ethers. So here an ether can be produced by two different methods. Two examples are given. We need to identify what is a better choice. One, the alkyl group, we have R and R prime. Two alkyl groups are there. So in one set of reactions, Rx, the alkyl halide is there, and the R prime sodium salt of the corresponding alcohol is there. In the other case, R prime halide is there and the sodium salt of the alcohol is there. So we have two different sets of alkyl halides and the alcohols. We need to identify which is the best condition for preparing this ether, and there is another ether. So here we have a tertiary butyl group and a methyl group. Here we have a cyclohexyl derivative and a ethyl derivative. So we have two sets of compounds. Let us see how we can efficiently make this compound. So for this particular cyclohexyl and the ethyl derivative, the best option is the alcohol is on the cyclohexyl unit and the halide is the ethyl halide. And in the case of tertiary butyl and methyl combination, we have the tertiary butyl as the alcohol and the alkyl halide is the methyl halide. We will now see why we have to choose this condition and not the other conditions. Now, if we look at this particular compound, the cyclohexyl unit and the ethyl unit, we have two ways of forming the ether bond. That is, there is a carbon here, CO bond is there. There is also carbon here and oxygen, so there is another CO bond. So between these two CO bond, breakage of one produces one set of starting materials, breakage of two produces another set of starting materials. So if we break from one, so this part, the oxygen will go with the other part. So in this case, oxygen, the alcohol unit is the ethanol unit and the halogen will be present in this particular unit. So we have a particular cyclohexyl halide is present. So here basically it is cyclohexenyl halide is present. But this reaction requires a strong base. So in this particular case, an alkoxide is used for the second step or the condensation of these two things. So that is a strong nucleophile and a base. So it always favors elimination reaction. So in other words, this particular cyclohexenyl derivative can undergo elimination reaction. So this combination is not the right combination. Whereas if we take the alcohol on this cyclohexenyl unit, then this alkyl halide does not undergo elimination. So this is the most preferred method for the formation of this particular ether. So always remember, whenever we choose the alkyl halide, because in this particular case we are not focusing on the alcohol, we are only focusing on the alkyl halide. The alkyl halide should not undergo elimination. So always the primary alkyl halide is the preferred choice if that exists. So in this particular case, this cyclohexenyl halide undergoes elimination because we use a strong nucleophile or a base. So let us go to the other one, that is a tertiary butyl and a methyl ether. So now you already know we cannot use the tertiary alkyl halide because this undergoes easy elimination. So this combination is not the preferred combination, and primary alkyl halide does not undergo elimination. So this primary alkyl halide and the tertiary butanol is the best combination for preparing this particular ether. Now we are going to prepare another set of compound. Here between the following two chloroalcohol, which one can form epoxide, and explain. we have a chlorohydrin. So this compound is a cyclohexyl derivative, and we have a chlorine here, we have a hydroxyl here. We again have a chlorine here, we have a hydroxyl here. Stereochemistry of these two carbons are given here. So from this we have to identify which one will give the corresponding epoxide, which one will not give the corresponding epoxide. So to solve this problem, what is required is, first of all, we need to draw the cyclohexane chair conformation. So by drawing the cyclohexane chair conformation, we can easily identify whether which of these two compounds can undergo elimination very easily. In other words, the ether formation here, especially the epoxide, is a cyclic ether in this particular case. So that means the hydroxide has to attack this carbon and the halogen has to leave. So this is the overall mechanism for this reaction. These two, chlorine and the hydroxyl, are present in the cis orientation, and in this compound the chlorine and hydroxyl are present in the trans orientation. That is, this is pointing upwards, this is pointing downwards. So that means they are in the opposite direction, or the trans orientation. So if we draw the cyclohexane chair conformation for these two compounds, so the chlorine is pointing upwards, the hydroxyl is in the equatorial position, this is in the axial position. So this is pointing upwards, this is also pointing upwards. So here the 1-2 cis orientation is axial equatorial orientation, and in this particular case we have the chlorine pointing upwards and the hydroxyl pointing downwards. In other words, these two are the trans orientation. So the 1-2 trans orientation is both the groups are axial. I have specifically put here axial because not the equatorial is also possible in this particular case, but for our elimination to happen, the axial orientation is the preferred one. So I have put it, or I have represented this as both axial orientation. Of course, we can also draw the equatorial chlorine and the equatorial hydroxyl. That arrangement is also possible. That is also again trans orientation, but the di-equatorial is not favorable for this particular cyclization. So we are choosing the diaxial orientation because both the diaxial and the di-equatorial can be formed by the simple ring flip. So in the first step, the hydroxyl, the proton is removed under basic conditions. So we form a oxide anion is formed. This oxide anion goes and attacks this carbon and the chlorine is removed. Because in this particular elimination to occur, what we need is anti-periplanar arrangement is required. Since the O- and the chlorine are not in the anti-periplanar arrangement, the elimination of the leaving group is not favored in this particular arrangement. Whereas if we look at this particular arrangement, these two are favored because they are in the anti-periplanar arrangement. So this elimination does occur. So here the elimination of the leaving group is favored. So this trans isomer gives the epoxide and the cis isomer does not give the epoxide. This is another example of how to synthesize the following ether, which you have already seen, and we can easily solve this problem. We have a benzyl unit here, we have a secondary carbon present here. So there are two ways we can make it. One is this particular alcohol moiety and the benzyl bromide. These two can combine together to give this particular ether, or this secondary alkyl halide and the benzyl alcohol the anion of the benzyl alcohol is also used. So we have two different combinations and we will have to see which one is the most preferred one. If we take this particular compound, here we have Sn2 reaction which will give our required final product, but this secondary alkyl halide can also undergo elimination. So this can undergo E2 elimination to produce this particular alkene. So in other words, we will be having difficulty in getting maximum yield of our required ether. So this combination is not a preferred combination, and this is the preferred combination where we have the alcohol on this secondary carbon and the benzyl bromide, because this cannot undergo elimination. So that's the reason this combination produces our required product. Now we have an alkene and we need to identify the product formed in the following reactions. We have two different conditions. This is permanganate, potassium permanganate and water, pH basic conditions, or osmium tetroxide and hydrogen peroxide. So this is basically for the dihydroxylation method. And another method is MCPBA, that is metachloroperoxybenzoic acid and water under acidic conditions. This again is a dihydroxylation conditions. So we have two different dihydroxylation conditions and we have to find out what is the product we will be getting. So treatment with MCPBA produces this particular cis isomer, and when this opens up we end up with a trans or anti-dihydroxylation is formed in this particular case. When we do permanganate or the osmium tetroxide based dihydroxylation, we end up with a cis or syn dihydroxylation. So these two methods are two different methods by which we can actually make cis isomer or trans isomer of the dihydroxylation method. Let us take up what we have studied so far. We have studied about preparation of ether, mainly the important method which is the Williamson ether synthesis method we have studied. We have also studied about reactions of ether. The most important one was the reaction with HX, and we also have studied about some worked out problem related to synthesis of ethers. With this we conclude this session. Thank you.